So, in the last class we saw how feedback, particularly negative feedback, desensitizes the forward transfer parameter, whatever it is, gain, with respect to active parameter variations. So, this is an important aspect of negative feedback amplifier design. Now, the second aspect of amplifier design, which we will now consider, is regarding linearity. This is the first aspect. The second aspect is linearity. What happens is that because of negative feedback, the system becomes more linear. It can handle larger signal levels, okay, at the input without distortion occurring. Now, how does this take place? Let us explain this to sort of illustrate how linearity is going to improve. V naught is going to be, let us say, G times V I before feedback. Now, this is not the case when nonlinearity comes into picture. V naught is then equal to, this is not the case, V offset, that is a function which is independent of V I, that is called offset voltage. Then we have linear output, okay. Then we have nonlinearities, which will be, okay, all terms like k 2 times V I squared, k 3 times V I cubed, all these things are nonlinearities. In the design of this we had earlier seen, these all these things, higher order terms, these are nonlinearities. Any amplifier is going to work in an active region where this is dominant and nonlinearities, this k 2, k 3, etc. are minimal. The operating point will be so chosen that V offset is 0, k 2 is very nearly 0, k 3 is very nearly 0, okay, for a certain signal level only. But as signal level increases, all these nonlinearities play their part. So, how in a negative feedback this can be reduced? I am considering only for voltage feedback. It is applicable equally well for current feedback or any other feedback. Now, this is illustrated here by taking now a feedback configuration here. This is not linear, it is governed by this function V naught and V I. This is governed by this function now, okay. This is non-linear, okay. So, now I give feedback H, okay. V I is going to be this, and this is only going to have error here, which is H times, okay, V naught. This is linear. We are assuming that this is non-linear and this is linear, okay, because this is made out of passive components here. So, we can afford to make this very linear. So, this error is nothing but V I minus H times V naught. So, instead of V I now we are going to substitute V I minus H times V naught. So, everywhere we have to only put here the error epsilon, epsilon squared, epsilon q. Okay. In a good feedback this error is going to towards 0. That means, this quantity is going to be made very small. What is this error? This is going to be V offset. This error G is V I minus H times V naught. This will write for this, and all these things are going to be still there. So, V naught therefore is equal to this. So, V naught into 1 plus G H, we will take this along with this, is now equal to V offset plus G by 1 plus G H into V I. Remember, this is what we got in the earlier feedback system. This offset is also going to be divided now. If I divide the whole thing by 1 plus G H, plus all this nonlinearity also is going to be divided by 1 plus G H. So, if the loop gain which is minus G into H here, okay, is very large, okay, then we can see here that V naught is going to be essentially, okay, equal to V I by H, what we got earlier also. Perfectly linear, and all these factors including offset will go towards 0. So, these factors will get very low, okay, because 1 plus G H is very high. Here this will become equal to 1 over H, becomes linear, okay, independent of G. So, this establishes very clearly that in any negative feedback system, the offset voltage is reduced after negative feedback, goes towards 0, and the nonlinearity is also reduced. The system becomes more linear. Now, this is an important aspect of, again, amplifier design. So, it can now handle larger signal level at the input before distortion can set in. One thing, however, you should note is the gain is reduced, okay, and therefore, the voltage level that is required at the input to bring the output to the same level as before is going to be higher, but even though it is higher, okay, for the same output level now you have lower distortion in the case of negative feedback amplifiers than in the case of open loop amplifiers. So, this is to be borne in mind. So, linearity is improved. And you will note that any improvement occurs by a factor of 1 plus G H, that means the loop gain factor comes into picture in every improvement that occurs in all these things. So, this is the second important conclusion that we arrive at, saying that in any negative feedback system, okay, the amplifier forward transfer parameter is desensitized with respect to variation in active parameters, number 1. Then it is also going to have low amount of offset voltage and nonlinearity associated with it. So, that means anything that we add externally now okay, all these things apart from the signal will get reduced. Even the noise generated is going to get reduced. Offset can be also treated similar to noise that is internally created, right. So, because this offset may be temperature dependent and okay, it might be varying with respect to time in an arbitrary manner. So, it is equal to certain amount of noise. So, even the noise okay, that is generated within the amplifier is also reduced by a factor dependent upon the loop gain. So, this aspect of amplifier design, negative amplifier feedback amplifier design, is an important criteria okay, which must be always borne in mind. Let us consider the third aspect of amplifier design. This is if, for example, G is not a sort of constant factor with respect to frequency, G is dependent upon frequency. Let us consider that there is a bandwidth connected with gain. So, G is equal to G naught divided by 1 plus let us say S by let us say bandwidth. So, this is saying that the gain function is going to have the gain constant at low frequency, but as frequency increases it will be falling at let us say a rate of 20 decibels okay, per decade okay, and that is a single pole system. So, here this is nothing but the bandwidth, and it falls to 1 over root 2 times G naught. So, this aspect we had considered when we discussed about amplifiers. This could be anything, gain, okay, trans resistance, trans impedance, voltage gain or current gain, it does not matter. Then what do? We give feedback. So, gain after feedback is equal to gain before feedback divided by G into H. So, what happens here? We can now consider that this is substitute for G this value G naught divided by 1 plus S by bandwidth. So, 1 plus G naught divided by 1 plus S by bandwidth okay, into H, which can be written as G naught by 1 plus S by bandwidth plus G naught H, dividing the numerator as well as the denominator by 1 plus G naught S, G naught by 1 plus G naught H divided by 1 plus S by bandwidth into 1 plus G naught H. The important factor to be noted, the gain with feedback okay, is equal to G f naught, which is G naught by 1 plus G naught H, which would have got if it is frequency independent. Okay. So, the gain with feedback, that divided by 1 plus S by new bandwidth okay, is old bandwidth into 1 plus G naught H. So, the bandwidth improves by a factor of 1 plus G H. I told you all improvements occur by a factor of 1 plus G H. So, bandwidth improvement so, if original amplifier, open loop amplifier with gain equal to G naught was usable up to bandwidth BW. This is usable up to a bandwidth of BW into 1 plus G naught H. If you note that gain into bandwidth of negative feedback amplifiers, what is the gain? This G naught into 1 plus G naught H is the gain of the feedback. So, G naught into 1 plus G naught H is the gain after feedback, and this is the bandwidth. Gain into bandwidth is a constant. Gain into bandwidth is a constant, G naught into GW. So, this factor into always a constant equal to G naught into bandwidth. So, whether this is another important conclusion in negative feedback. The gain into bandwidth remains always a constant. That means, if I have an open loop amplifier with 1 megahertz bandwidth having a gain of 1, that will have a bandwidth of 100 kilohertz when it has a gain of 10. Is this clear? When it has a gain of 10, it has a bandwidth of 100 kilohertz. When it has a gain of 100, it has a bandwidth of 10 kilohertz. When it is a gain of 1, it has a bandwidth of 1 megahertz. So, gain into bandwidth is a constant factor. So, these three are the three important factors associated with negative feedback. What are they? Sensitivity number 1, linearity number 2, bandwidth improvement number 3. So, we will further consider the same effect in general in the case of the parameters H, Y, Z and G. These are the basic amplifier configurations. What happens in the case of H, Y, Z and G? What are the different types of feedback which are possible as far as the feedback is negative, and how things improve in the case of the various parameters. Let us now consider the two-port network that we had earlier used for discussing amplifiers. We said amplifier, ideal amplifier has two ports, input port and output port, and can be categorized as belonging to 4 types of control sources: voltage controlled voltage source, current controlled current source, voltage controlled current source and current controlled voltage source. And these ideal amplifiers belonging to these 4 categories can be only uniquely defined by one of the 4 parameters. For example, G parameter will ideally define a voltage controlled voltage source, ideal. H parameter will ideally define a current controlled current source, and Y parameter will define a voltage controlled current source. Z parameter will define an ideal current controlled voltage source. So, these ideal sources, control sources, can be only defined by these parameters respectively. This we had understood in the beginning of the course. Now, how do we give feedback to these amplifiers which are non-ideal? Let us say, therefore, we have a situation of non-ideal control sources. So, when voltage controlled current source is non-ideal, or current control voltage source is non-ideal, or current control current source is non-ideal, or voltage control voltage source is non-ideal. What does it mean? For example, voltage control voltage source is non-ideal. What it means is the matrix parameter 0 0 0 and GF, this is the ideal way to represent. That means input admittance is 0 or input impedance is infinity, output conductance, okay, that is output resistance is, it is voltage source 0, okay, output resistance, then reverse transfer parameter is 0. Now, if it is non-ideal, these are non-zero factors. Close to low value, this will be large, but these will be low values. In such a situation, in order to convert each one of these non-ideal sources into ideal sources, negative feedback can be applied. This is the important. Convert non-ideal sources into ideal sources, okay, apply negative feedback. Apply negative feedback. Why? To convert, okay, non-ideal sources into ideal sources. Once again, let me explain. A non-ideal source here will always have all the other parameters 0 except the forward transfer parameter, which is going to be large, huge. Now, in the case of ideal non-ideal sources, these will become finite, but non-zero. So, we want to make this go towards 0, then we have to apply appropriate negative feedback. So, this is the important function of negative feedback. How do we apply negative feedback? Now, if I apply H feedback, okay, let us see. How do I apply H feedback? This kind of thing is defined very easily by the definition of this itself. Okay. H feedback, what is HI? Okay. HI is input impedance, okay, with output shorted. Okay. So, input impedance. So, impedances add in series. Okay. So, immediately you can conclude that the amplifier network and the feedback network, they should come in series at the input. What is happening at the output? At the output, okay, it is going to be again a voltage source. That means output impedance should come down, input impedance should go up. Input impedance should go up, output impedance should come down. That is what this says. So, it should be in series at the input and in shunt at the output. So, in order to realize a voltage controlled voltage source, the input impedance should go up, output impedance should come down. So, it should be in series at the input in order to increase the input impedance. It should be in shunt at the output in order to bring down the output impedance, in order to make it a voltage source. So, this is nothing but H feedback. So, in order to realize, okay, a voltage controlled voltage source which is expressed in terms of G parameters, you have to give H feedback. So, you have to give H feedback in order to obtain a voltage controlled voltage source. Is this clear? Now, mathematically also it becomes clear. The H parameters add, okay. Here for this amplifier, since these are in series at the input and shunt at the output, H parameter of this will add with H parameter of this. So, composite H parameter of this structure is going to be H parameter of this plus the H parameter of this. So, let us consider I am giving H feedback, in which case H parameter of the amplifier and H parameter of the feedback network, okay, these simply add, or I can write the composite H parameter as HIA, okay, plus HIF, okay, and H naught A plus H naught F, okay, H F A plus H F F, okay, and H R A plus H R F. That means these are simply adding up. This is a very easy technique to obtain the composite parameter. If this is in series at the input and shunt at the output, then you know that it is H feedback, and simply take the H parameter of amplifier and add it to the H parameter of the feedback network. Then what happens? This is the composite H parameter. How will you convert into G? Then you will take the matrix here, okay, you can invert, right. So, you will take the matrix of this delta H, okay, determinant of this, okay, and obtain the G parameter. What will be the G I? Okay. What will be the G I? G I is going to be, okay, is going to be H naught A plus H naught F divided by delta H, okay. G O is going to be H I A plus H I F divided by delta H. What is delta H? Delta H is the determinant, which is H I A plus H I F into H O A plus H O F minus H R A plus H R F, H F A plus H F F. This is the determinant. So, H G I and G naught get modified, and what is going to be G F is going to be minus H F A plus H F F divided by delta H, and G R is going to be minus H R A plus H R F divided by delta H. So, this is nothing but the matrix inversion, right. So, delta H is a constant factor coming in all the parameters. If delta H is very high, what is delta H? It is nothing but this, which can be written as 1 minus H R H F by H I H O, okay, into H I H O. So, this delta H is nothing but 1 minus, I am taking H I into H O, this is composite H I, this is composite H O, H I into H O, it is 1 minus H R into H F divided by H I into H O. This is similar to your 1 plus G H factor. So, this is called the loop gain. The loop gain is equal to minus H R H F divided by H I into H naught. This is called the loop gain. This we called as minus G into H. It is the same factor by which all the parameters change, right. So, if you notice here, this factor, okay, divided by delta H involves this factor divided by delta H everywhere, okay, the loop gain comes into picture. If the loop gain is very high, that means this is going to be very high and it is negative, right. Okay. So, then it is negative feedback. Is this clear? So, this is an important aspect of this thing, right, our amplifier design. So, loop gain is really HR HF divided by HI into H naught. If this is negative, okay, then this becomes positive, okay, and this is negative, it is negative feedback. If it is positive, okay, it is positive feedback. So, this aspect of design is important, right. Now, let us summarize the whole thing. If loop gain, what is loop gain? HR HF divided by HI into H naught. This is called the loop gain. This is negative, then it is negative feedback. If it is positive, it is positive feedback. Okay. Okay. So, loop gain, if it is very high, is much greater than 1 and it is negative feedback, then you will note that all these parameters which are getting modified. Let us see. The first parameter is that this is H naught divided by HI H naught into 1 minus HR HF divided by HI into H naught. This is the GI. Okay. This is equal to GI. Earlier we had written the same thing. So, H naught gets cancelled with H naught. See what happens to the parameter. GI is equal to 1 over HI into 1 minus HR HF by HI H naught. Right. So, input impedance increases. Okay, this is input impedance. It increases because these are coming in series and therefore, GI goes towards 0. This factor is going to become very high. Therefore, this 1 over this, okay, goes towards 0 because of negative feedback. So, this is GI and the other factor here is going to be minus HF divided by HI H naught into 1 minus HR HF by HI H naught. This is going to be our GF now. So, if this factor is very large compared to 1, we can ignore 1, right. So, we can ignore 1. So, what happens? HI H naught gets cancelled with HI H naught, HF gets cancelled with HF, this becomes plus and therefore, the entire GF becomes equal to 1 over HF, HR, right. So, this is an important thing. This whole thing goes to 1 over HR. And what is HR made up of? Please remember, it is composite HR, HR amplifier plus HR feedback. So, HR amplifier plus HR feedback. So, HR amplifier is very nearly 0, there is no feedback in the amplifier, it is feed forward structure. So, this is very nearly 0. So, HR feedback network is what fixes up the GF. So, this is an important aspect of negative feedback. The input impedance goes up, we have demonstrated here. The forward transfer parameter gets stabilized at a value corresponding to 1 over HRF, right. And next consider what happens to the other two parameters. So, GR is equal to HR divided by HI H naught into again 1 minus HR HF by HI into H naught. We have already assumed that HR HF by HI H naught is very large compared to 1. Therefore, we can ignore this 1, this is minus, okay. We can ignore this 1. So, this becomes plus plus HI H naught gets cancelled with HI H naught, HR gets cancelled with HR. So, GR is equal to 1 over HF. HF is a huge quantity, right, already. So, 1 over HF is going towards 0 very clearly. Then G naught, the other parameter, is equal to HI by HI H naught into 1 minus HR HF by HI H naught. So, once again you can see that H naught is the output conductance originally before feedback, and it is going to improve by H naught into 1 minus HR HF by HI H naught. It is going to get boosted up. The conductance is going to increase. That means the resistance, which is G naught, is going to decrease, goes towards 0. It becomes an ideal voltage controlled voltage source. Okay. The output impedance is going towards 0 means it becomes a voltage source. So, all the parameters, okay, go towards 0 except the forward transfer parameter. So, we have now seen that all parameters go towards 0, okay, by negative feedback of the proper kind, H kind, in order that it becomes an ideal voltage controlled voltage source. So, we started with a voltage controlled voltage source, okay, which had non-ideal factors here. These are not non-zero, this was high, and we wanted to make it a good voltage controlled voltage source. Then we gave H feedback, remember, right. So, this impedance, okay, this is actually conductance in G parameter. So, this impedance improved, that means conductance decrease. This resistance, okay, decreased to 0 because conductance increased by a factor corresponding to the loop gain. This went further towards 0, okay, and this got stabilized, okay, became insensitive to active parameters, became dependent only on the passive parameter. So, this is the story of every negative feedback structure. First of all, how do we recognize whether it is negative feedback or not? The loop gain should be negative, that is what we established earlier also. Okay. In this particular case, the loop gain corresponds to HR HF divided by HI into H naught, that should be negative. Now, if I want an ideal current control current source, what kind of feedback should I give? It is current control, okay. That means it should go towards short circuit. It is current source, its output impedance should get boosted up. It should become a short circuit at the input, output impedance should increase. That means things should be in shunt at the input and series at the output, which means it is, okay, G feedback. This was H feedback. In order to obtain an ideal current control current source, I must apply G feedback. What is G feedback? This is H feedback, okay. G feedback, I put things in shunt at the input and I connect things in series at the input. So, this is where I feed the voltage source, and this is where I connect the load now, and this is the composite G feedback. What are you doing here? You are trying to realize an ideal current control current source, because we had a non-ideal current control current source. Okay? Non-ideal, because these were non-zero and we wanted them to go towards 0. Okay? Then we apply G feedback. Why G? Because we wanted to reduce the impedance at the input so as to make it current control and increase the impedance at the output so that it becomes a current source. So, this way if you understand feedback, okay, you will never commit the mistake of connecting these things wrongly. Right? Now, what is the feedback in order to make it a voltage controlled current source and current controlled voltage source? Okay. So, voltage controlled current source, okay, this is expressed in terms of Y parameter. That means amplifier will be 0 0 0 Y F amplifier. So, I should start with Z, that means feedback is Z. How is this? Y feedback, this is G feedback. So, now we will make it Y feedback. It will be series at the input, okay, and series at the output. This is Z feedback. What does it result in? Ideal voltage control current source. What happens? Input impedance increases because it is voltage control, output impedance increases because it is current source. Okay. So, you put things in series at the input and series at the output, okay, and Z parameters add, then convert it into Y parameter. In the Y parameter same thing happens, all the other parameters like Yi, Yr and Y0 will go towards 0 and Y of will become independent of the active parameter. It will depend only on the passive parameter. Okay. Finally, we have the Z feedback, that is Y feedback, this Z configuration. Amplifier has Z of A ideal, but these are non-zero. So, we want them to go towards 0. So, we apply Y feedback. What is Y feedback? Things are, it is to be made a current controlled voltage source. Impedance at the input should go down, impedance at the output should go down, voltage source. So, it should be shunt at the input and shunt at the output. Shunt at the output. This is what is called Y feedback in order to realize current controlled voltage source. So, this in general tells us about how we can tackle negative feedback in two-port networks. Let us summarize the whole thing. There are 4 types of feedback. These are Z feedback, Y feedback, G feedback, H feedback, respectively giving if they are negative and they have respectively high loop gain, okay, when given feedback, then they are going to realize respectively Z feedback realizes Y network idealization, which is a voltage controlled voltage source. Y feedback realizes Z network, which is a current controlled voltage source. G feedback realizes H network, which is a current controlled current source. H feedback realizes G network, which is a voltage controlled voltage source. Now all these things, okay, in general the loop gain is always defined by, okay, PR PF divided by PI PS P naught. What it means is PR could be H, Y, Z or G, okay. Again PF could be H, Y, Z or G. So this is emittance matrix representation which I had talked about. So loop gain is always PR PF by PI into P naught. If you take the source effect into consideration at the input and load effect into consideration at the output, the loop gain is in general, loop gain in general in any one of the parameters is always equal to PR into PF divided by PS plus PI into P naught plus PL. It just depends upon whether the parameters are Z, Y, G or H. In all these things it is the same. Then if this factor is negative, then it is negative feedback. If it is positive, it is positive feedback. Then the factor by which things improve will always correspond to 1 minus the loop gain. This we had seen. The factor by which things improve. If things are in shunt at the input, the admittance level goes down, okay, by a factor determined by this. If things are in shunt at the output, again, okay, the admittance increases, the impedance level goes down by a factor determined by this. If things are in series at the input, the impedance level will increase or admittance will go down, okay, by a factor determined by this. If things are in series at the output, again the impedance level will go up. It is going towards current source realization. The factor by which it improves is again the same thing. So this is the consistent way we can define all types of feedback and also know what are we aiming for. Are we aiming for design of an ideal voltage controlled voltage source? Are we aiming for an ideal current controlled current source? Are we aiming for an ideal current controlled voltage source, or are we aiming for an ideal voltage controlled current source? In all these things, since the forward transfer parameter is desensitized with respect to active parameter, naturally the bandwidth also is going up. Desensitization simply means desensitization with respect to everything, temperature, time, frequency, everything. So even with respect to frequency, okay, it is insensitive or its bandwidth is improved. Corresponding to this, the bandwidth of G of A is improved. Corresponding to this, bandwidth of HF is improved. Corresponding to this, bandwidth of YF is improved. Corresponding to this, bandwidth of ZF is improved. This is what you have to remember, that if it is voltage controlled voltage source, it is only the voltage gain whose bandwidth is improved, not the current gain. Current gain may not have its bandwidth improving, okay. The purpose is not that. Similarly, if it is current controlled current source, it is only the current gain whose bandwidth is improved, okay. May not be for voltage gain. This is again something that you have to understand. Again, if it is Z or Y feedback corresponding to impedance and admittance, the bandwidth is improved, may not be for the gains, okay. So this is what is to be digested clearly before we go further with examples on these negative feedback, specific examples on negative feedback, as long as you have understood the two port network theory involving negative feedback.